continue our discussion on mathematical induction. In the last lecture, we have studied mathematical induction and some problems related to mathematical induction. Now, we will start by giving another alternative and interestingly equivalent version of the principle of mathematical induction, which is called the strong mathematical induction. At this point, it is worth mentioning that the original mathematical induction that we studied in the last lecture and the strong mathematical induction that we are discussing now are equivalent, but sometimes depending on the problem, the first version is more useful and sometimes the second one, that is the one which we are going to study now, becomes more useful. Now, let us first see what is meant by strong mathematical induction. Let P n be a statement which for each integer n may be either true or false, then P n is true for all positive integers if there is an integer q greater than or equal to 1 such that 1 P 1, P 2, P q are all true to when k is greater than or equal to q, the assumption that P I is true for all integers 1 less than or equal to I less than or equal to k implies that p k plus 1 is true. So, here we see that our hypothesis and assumptions are slightly different than the previous one. What we prove here, what we have to prove in the beginning is that there is a positive integer q which is greater than or equal to 1, for which p 1, p 2 and p q are all true. That is, we have to show that for a positive integer, any positive integer less than that will satisfy p n. Then our assumption is that we take a we take a k greater than or equal to q and assume that for all I between 1 to k, p I is true, and then we have to prove that this implies that p k plus 1 is true. If we can do this, then we claim that the statement p n is true for all n greater than or equal to 1, and this is what we mean by the principle of strong mathematical induction. As I have already said, that the two principles are exactly same, they have the same power, but we use either of them depending on the problem under consideration. Now, let us check the steps of the proof or steps of a proof involving strong mathematical induction. The steps of a proof involving strong mathematical induction. So, first, like before, we have basis of induction, basis of induction show that p 1, p 2, p q are all true. To strong inductive hypothesis. Assume that p I is true for all integers I such that 1 less than or equal to I less than or equal to k, where k is greater than or equal to q. Now, if you compare the previous version, there we assume that p k is true for some k greater than or equal to n 0, and we proved that n 0 p n 0 is true, and then we went on to prove that p k plus 1 is true. In this case, we assume that for all I between 1 to k, where k is greater than or equal to q, p I is true, and then we go on to prove this in the inductive step. Show that p k plus 1 is true on the basis of the strong inductive hypothesis. Now, before we go on to discuss some examples where strong mathematical induction is useful, we will quickly have a look at recursions and how we define recursions. Let n be the set of non-negative integers a function from the set of non-negative integers is defined recursively if the value of f at 0 is given and for each positive integer n, the value f n is defined in terms of the values of f at k, where 0 less or equal to k less or equal to n. Now, we look at some recurrence relations, and the probably the most famous recurrence relation, that is the Fibonacci sequence. F0 is defined as 1, which is equal to F1, and f n plus 1 is f n plus f n minus 1 for all n greater than or equal to 1. This is how we define Fibonacci sequence recursively. So, let us start calculating the elements of the sequence. So, as we see, for 0 f 0 equal to 1, then for 1 f 1 equal to 1, then for 2, this value is f 0 plus f 1, which gives me 2. Then for 3, this value is f 2 plus f 1, that is 2 plus 1, which is equal to 3. For 4, this is f 3 plus f 2, which is equal to 2 plus 3 equal to 5, and so on. Now, it is known that the nth Fibonacci number, that is f n, is given by one over root of 5, then 1 plus square root of 5 over 2 whole raised to the power n plus 1 minus 1 minus square root of 5 over 2 whole raised to the power n plus 1 for all n greater than or equal to 0. And we would like to prove this relation by using strong mathematical induction. Proof. Now, let us put n equal to 0. If we do that, then f 0 is 1 by root 5, and here it will be 1 plus square root of 5 divided by 2 minus 1 minus square root of 5 divided by 2. This is equal to 1. For n equal to 1, we have f 1 equal to 1 by square root of 5, and this is 1 by square root of 5 over 2 and square minus 1 minus square root of 5 by 2 square. Now, this is equal to 1 by square root of 5 and 1 plus square root of 5 plus 1 minus square root of 5 whole divided by 2 into 1 plus square root of 5 minus 1 plus square root of 5 by 2, yes, and therefore, here it will get cancelled and this factor is equal to 1, whereas this factor is equal to square root of 5 and this gives me 1. So, we have checked that our formula given here works for n equal to 0 and n equal to 1. Now, we go for the induction hypothesis, which in this case becomes strong induction hypothesis for n greater than or equal to 1. Assume that f k equal to 1 by square root of 5 into within bracket 1 plus square root of 5 divided by 2 raised to the power k plus 1 minus 1 minus square root of 5 divided by 2 raised to the power k plus 1. Yes, for each integer k, for each integer k where 0 less than or equal to k less than or equal to n. Now, once this is my induction hypothesis, I go for the inductive step. Inductive step. We start with f n plus 1. The question is why f n plus 1 and not f k plus 1. So, we go to the induction hypothesis and we see that here we have assumed that I have an n, and for all k from 0 to n this formula works, and I am now checking for n plus 1. If I am successful in proving that this formula works for f n plus 1, that means for all k between 0 to n plus 1 the formula works, and therefore, we can start checking for n plus 2, but that is of course, that will work by using the same argument, because we are able to choose n any positive integer greater than 1 and fix it. So, we now have f n plus 1, and if we use the basic recursion formula, we know that f n plus 1 is equal to f n plus f n minus 1, and since in both these cases the subscript n and n minus 1 are less or equal to n, we can write by using the induction hypothesis that (1 by root 5) 1 plus root 5 divided by 2 n plus 1 minus 1 minus root 5 divided by 2 n plus 1 plus 1 by root 5 1 plus root 5 raised to the power n minus 1 minus root 5 by 2 raised to the power n. Now, for convenience, we replace 1 plus root 5 upon 2 by a and one minus root 5 divided by 2 by b, and the expression will become a to the power n plus 1 minus b to the power n plus 1 plus a to the power n minus b to the power n, which in turn becomes 1 by root 5 a to the power n a plus 1 minus b to the power n b plus 1. Now, if we start with a plus 1, we will see that a plus 1 is equal to 1 plus root 5 by 2 plus 1, which is of course equal to 1 plus root 5 by 2 and 1 plus root 5 plus 2, which after simplification becomes 3 plus root 5 by 2, and by a sudden streak of imagination, if we are able to check a square, that is 1 plus root 5 upon 2 whole square, which is equal to 4 in the denominator, and in the numerator 1 plus root 5 whole square, which gives us 4, 1 plus 5 plus 2 root 5, which brings us to 6 plus root 5 divided by 4, which is 3 plus root 5 divided by 2. I said that we need imagination. Somehow we have to guess the right thing, and to realize that what we get for a plus 1 is same thing as a square. So, this is of course a plus 1. Similarly, we will see that b square equal to 1 plus b, and if we replace these two expressions in the calculation of f n plus 1, then I get 1 by root 5 equal to a to the power n into a square. So, that gives me a n plus 2 and minus b n plus 2, and which is which shows me that the formula works for n plus 1, and therefore, our proof is complete. From this we can say, thus the formula of f n works for f n plus 1, hence our proof is complete. thus, we have seen one example using the principle of strong mathematical induction. Now, let us look at another problem which uses the principle of mathematical induction, and it is a problem related to postage stamps. Suppose that we have stamps of 2 different denominations. Rupees 3 and rupees 5. To show that it is possible to make up any postage of rupees 8 or more by using these two stamps. To show that it is possible to make up any postage of rupees 8 or more by using the stamps of these denominations only. Now, to solve this problem, we start from the beginning. If we have a postage of rupees 8, of course, 8 can be written as 3 plus 5. Now, let us check 9. 9 can be written as 3 plus 3 plus 3. 10. 10 can be written as 5 plus 5. Now, if we come to 11, 11 can be written as 5 plus 3 plus 3. So, we see that at least for first few consecutive possible postages, we can make up those postages by using the denominations of rupees 3 and 5. Now, the question is that is it always true? Then we can say that let us use mathematical induction. We have already proved the basis of induction. So, basis of induction rupees 8 postage can be made up of the denominations rupees 3, rupees 8 and no, rupees 3, this is rupees 3 and rupees 5, of course, because 8 equal to 3 plus 5. Now, we go to the induction step. No, we go towards induction hypothesis. Assume the result to be true for a postage of rupees k where k is greater than or equal to 8. Now, we come to induction step. In the inductive step, we have two cases. Case 1, to make up the postage k at least 1 rupees 5 stamp is required. What do we do then? Replace the rupees 5 stamp by 2 stamps of rupees 3. If we do that, then we see that 5 gets replaced by 6 and therefore, the total postage will be k plus 1. The postage will be k plus 1. Now, we come to case 2. Now, in the case 2, all the stamps required to make up the postage of k is of denomination 3. So, there is no 5 denomination 5 stamp. So, in this case, all the stamps are of denomination rupees 3. Now, what we realize over here is that this postage cannot be 8. So, it can be 9, in which case it is 3 plus 3 plus 3 9, and if it is something more than 9, then also it will have at least 3 stamps of denomination 3. In this case, there must be three stamps of denomination 3, rupees 3. Now, our strategy will be to replace these 3 stamps by 2 stamps of denomination 5. So, replace them, that is all the 3 stamps, by 2 stamps denomination 5 rupees 5 to obtain a postage of rupees k plus 1. Now, we see that this is exactly what we wanted. We wanted to show that if we have a postage of k, and if we can make up a postage of k by using stamps of denomination 3 and 5, whatever the case may be, I can make up a postage of rupees k plus 1. Once we have proved that, and we know that we can make up postage of 8, therefore, by mathematical induction we know that we have got the complete proof. The last problem in this lecture on mathematical induction is involving chessboards. Now, let us consider an 8 by 8 chessboard. Well, this is an 8 by 8 chessboard, and suppose we take out one block from it, suppress one block or square from it, then we will call this a defective 8 by 8 chessboard. Defective 8 by 8 chessboard. Now, there is another object that we would like to introduce, which is called a triamino. It looks like this. The question that we are asking is that can I cover this 8 by 8 chessboard by using triaminos of this type? Let me correct myself. My question is that can I cover a defective 8 by 8 chessboard by triaminos, or in general is it possible to tile an n by 2 to the power n by 2 to the power n by n defective chessboard by triaminos? Question. Is it possible to tile 2 to the power n by 2 to the power n defective chessboard by using triaminos? Now, we will try to use mathematical induction. Suppose we take n equal to 1, then I get a 2 by 2 chessboard, and I know that I can tile it by triamino. Suppose because of being defective this shaded square is excluded, then whatever is left is a triamino. It does not matter which square I leave out. If this square is this, then I can place the triamino like this, or if the square is like this, then I can place the triamino like this, or if the square is over here which is removed, then the triamino will be kept like this. So, I can put any triamino, one triamino, and by tiling I mean that I want to cover the chessboard by triaminos, and distinct triaminos must not intersect, that is they must not overlap. That is something that we have to be careful, and for n equal to 1 I say that I have only single triamino. So, I can do this without any overlap. Now, the question is that what about a 4 by 4 triamino, what about a 4 by 4 chessboard, defective chessboard. So, n equal to 2. So, I have got a situation where I have got 4 by 4. So, this is 2 square by 2 square chessboard, and let us suppose that I put a defect over here. Now, we see over here is that a 4 by 4 chessboard is made up of 4 2 by 2 chessboards, one here, this is 2 2, and this is 2 2 2 2 2 2. So, we have got 2 by 2 chessboards over here. 4 2 by 2 chessboards are giving me one 4 by 4 chessboard, and if we want to go in general, we will see that 2 to the power k plus 1 by 2 to the power k plus 1 chessboard is made up of 4 chessboards, each of which are 2 to the power k by 2 to the power k. All right. Now, we know that there is a defect. So, the defect in the 2 to the power k plus 1 by 2 to the power k plus 1 chessboard has to lie in one of these smaller chessboards. Suppose it is here. Then what we can do is that we can put a triamino around the center here, making the remaining 3 chessboards defective. Now, let us assume that 2 to the power k defective chessboards can be tiled by triaminos, then this one can be tiled, 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 and of course, this one can be tiled because this is defective from the beginning, and therefore, the whole chessboard can be tiled. So, if we assume that tiling is possible for k, we have proved that tiling is possible for k plus 1. Assuming that the tiling is possible for k, we have that is, to be more precise, 2 to the power k by 2 to the power k defective chessboard. Let us write more precisely. So, 2 to the power k by 2 to the power k defective chessboard, we have proved that it is possible for 2 to the power k plus 1 by 2 to the power k plus 1 defective chessboard, and we have already seen that tiling works for n equal to 1. Therefore, we know that if we have a 2 to the power n by 2 to the power n defective chessboard, no matter how large n is, we can tile it, and of course, in that case we can tile an 8 by 8 chessboard. And that is all for today. Thank you.